Vector algebra's hidden boundary. It's time to jump into the mathematical principle that sets an upper limit on vector addition, revealing the intricate connection between geometry and algebra. In this question, we're tasked with proving the triangle inequality, which is, as stated, the sum of vector alpha plus beta in the norm, that is, its magnitude or length, is less than or equal to the length or norm of vector alpha plus the length or norm of vector beta. Now, the triangle inequality is a fundamental principle in analysis and geometry, and it asserts this statement here. For any vectors alpha and beta in the inner product space V, this inequality encapsulates the geometric notion that the sum of the lengths of any two sides of a triangle must be greater than or equal to the length of the remaining side, while also demonstrating that vector addition of length is not linear. And graphically, we could see that if I add vector v with vector w, which using the head to tail method, we get this resulting vector known as v plus w. And we clearly see that the green and the blue vector have more length than the red vector here. So this is what we're tasked with proving, because it's not what you know, it's what you can prove. And that is the goal of this video. So to initiate this proof, let's define gamma, kind of like we saw a couple questions ago, as the addition of alpha plus beta, representing the sum within the norm on the left side of the inequality. From here, what we note is that within the norm, if I square both sides, which we're doing so to make it easy on us, as not have to deal with more square roots. So if we're going ahead and squaring the norm, what we see here is that alpha plus beta, which we represent by gamma, this squaring allows us to use the inner product, which once again is turning out to be a powerhouse in vector or in linear algebra and its concepts. So going ahead and substituting in the gamma definition on the right-hand side, leaving the left-hand side for later, what we see is that by equation A.21, we can go ahead and distribute thanks to linearity, and that's what we see here, gamma with alpha, gamma with beta, and by going ahead and taking the conjugate via A.19, we could switch the order. So gamma alpha goes to alpha gamma and beta gamma. Again, we can do this because we're living in a complex plane or a complex vector space because the components are complex. So in order to switch them, we have to go ahead and set up that asterisk. So with that, we can now plug in gamma on the right-hand side, or if you want, you can do that initially, put in alpha beta here, and then distribute that way too. Either way it goes, you're going to get the same algebraic representation. And the way that, because you're dealing with complex numbers, this author likes using real and imaginary arguments to give you the more general landscape of things, especially in the quantum mechanics context. But there's several other proofs of this, which I include in the PDF for the patrons. That being said, after we plug in the gamma here, we still need to distribute this just like we did from 8.21. And this is what we see in the distributed form. Alpha with alpha, alpha with beta, beta alpha, beta beta. Now our goal is to simplify this down and make a couple clever tricks happen, and then we could see the inequality happen in real time. So now that we go ahead and we found the distributed inner products, now we have this. But note that the conjugate was on the outside of the brackets, which means that we can apply it to every part in the bracket. So all of these are conjugated. Now, using our old friends, we can go ahead and switcheroo here. Note that it doesn't matter because we're in the same inner product. Then alpha to alpha, beta to beta there, crisscross, crisscross, and we're good to go. From here, we can put the inner products of the same vectors close together because that's what's going to come in real time and make our lives happy. And then we see that we have this alpha beta here and that beta alpha here. And now we can reconstitute or restate our inequality, or not inequality, but the norm statement that we had earlier. So the sum of alpha beta squared brings us to the distributed form here, which is what you could have started with originally if you didn't want to use the gamma to clear things up and show you piece by piece. Both are totally fine. But as a result, what we see, this is pretty easy. This is pretty easy. What we need to do is figure out what these cross terms are doing. And that's where we use this nice little clever tool. The fact that the components of alpha and beta are complex, meaning that they could be all real or all imaginary or some combination of the two, we know that the addition of alpha beta plus beta alpha in the inner product, we can go ahead and rewrite the second term in terms of its conjugate, and we get a replica of the same thing, alpha beta, and as a result, we can say, well, okay, the two things here are going to be, if we look at the real parts, we have two of the same thing. What this conjugate tells us that we have opposite and imaginary parts for these two products. So if I'm looking at the real parts only, I have two of them, and that's true. However, because we're looking at just the real parts, we can't have the full picture of the scope of length, because if we're only looking at the real axis, that leaves us the imaginary axis untouched. So this 2 times this real has to be less than or equal to 2 times the magnitude of one of these by itself. And this is the key to unlocking this proof here, given that we're dealing in complex numbers in the complex vector space. So with this being narrowed down to a singular inner product, we can apply the Schwarz inequality, which we had just run through 2 questions ago, which stated that the magnitude squared of the inner product is less than or equal to the inner product of alpha times the inner product of beta with itself. And so by taking a square root, we can get just the magnitude of alpha beta by itself. Of course, that square root's going to be gross to deal with, so we'll have to do some clever algebra to clean it up. That being said, how it applies to us is that the 2 real part, which is less than 2 times the magnitude of the inner product, well, since we know what the magnitude is, we can plug that in here. And now we invoke a square root with an alpha beta, which ties in perfectly with what we had before. That being said, applying this result to our norm equation yields the norm squared here, alpha beta, and the addition, our terms here, alpha beta, and now we see that this was what we set the original inequality to because of the 2 times the real part argument. From here, we can go ahead and plug in alpha right there, just bring it all down. Put this as a substitution for the square root that we just walked through. Note that we have 2 of them, and now we can let the games begin on simplifying. So going back to the definitions from 8.22, this inner product is actually the norm squared, or the magnitude squared. As a result, we have the norm squared here for alpha, norm squared for beta. This alpha here, norm squared, beta here, norm squared. But since we have 2 things that are squared multiplying each other, we could write the square on the outside. As a result, this square and this square root cancel each other, and right on time, we get that thing and that square root cancel out, so we're good to go. Moving forward then, we see that we have norm squared alpha beta norm squared plus 2 alpha beta in both their norms. These look like the cross terms of a binomial expansion, so we can go ahead and factor that out into a closed form of the norm of alpha plus the norm of beta squared. This is perfect because now, since both are non-negative, this thing and this thing are non-negative, we could cancel the 2's on them. And the canceling of the 2's, as we see here and here, lead us directly to the triangle inequality that we were trying to prove. Thus, we again have the proof that we need to show that although I add 2 vectors, some parts of those may cancel out. So that added vector length is less than the sum of the other 2 lengths. So that's pretty cool. Very, very helpful, and we've seen this be applied in a million different cases in any one analysis class. Very, very important. So another great proof video. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment now to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.